Welcome. In this class, we shall consider about the ratio estimators. Now, in many surveys, information on auxiliary variable, which is highly correlated with the study variable, is readily available and can be used for improving sampling design. Stratified sampling and PPS schemes are two such examples. In stratified sampling, we use the auxiliary information for stratifying the population, and also in PPS sampling, we use auxiliary information to find the probabilities of selection. In both the cases, we require the information of the auxiliary variable for each and every unit of the population prior to our study. But this information may not be available always. Instead, we can get the information on the population mean or the aggregate, that is population total of the auxiliary variable, and this information can also be utilized to develop more efficient estimators, just like a ratio method of estimation, product method of estimation, and a regression method of estimation. Now here we shall consider the ratio method of estimation, ratio estimators. So let us denote yi as the value of the characteristic under study for the ith unit of the population, xi the value of the auxiliary variable x for the ith unit, y is the population total for the study variable, and x, this is the population total for the auxiliary variable, and similarly y bar, that is population mean of the auxiliary variable, of the study variable, and x bar, this is the population mean for the auxiliary variable, and we denote r, that is the population ratio. This is y by x, or this is also equal to y bar divided by x bar. Let rho is the correlation coefficient between x and y, that is study variable and the auxiliary variable in the population. Now, in order to estimate y, that is population total or population mean or population ratio, we select a sample of size small n from the population. Let we use the simple random sampling without replacement scheme for selecting the sample. And suppose y bar and x bar denote the sample means of the study variable and the auxiliary variables respectively. So y bar, that is equal to 1 by n summation I equal to 1 to n yi, and x bar, that is equal to 1 by n summation I equal to 1 to n xi. Now we assume that x bar, the population mean, or x, population total of the auxiliary variable x, is known to us. So the ratio estimators for estimating population ratio R is given by R cap, that is equal to y bar by x bar, that is equal to y bar cap divided by x bar cap. Estimate of, that is equal to estimate of y bar divided by estimate of x bar. Now for estimating population mean y bar, the ratio estimator is given by yr bar, that is equal to y bar into x bar, capital X bar. Capital X bar is known to us. So that is equal to y bar into x bar by x bar. Similarly, for estimating y population total, we have to define y cap, that is equal to n y r bar, that is equal to n y bar x bar by x bar. So these are the ratio estimators. Now we have to find the bias of the ratio estimator. Now we have the ratio estimator for estimating the population mean, that is y bar, that is equal to y bar into capital X bar by small x bar. This is also sometimes we can write y bar by x bar into x bar. This is the ratio of two sample means, that is why it is the ratio estimator. Now we can see expectation of yr bar equal to expectation of y bar by x bar into x bar. So this is not equal to expectation of y bar by expectation of x bar into x bar. So that is equal to y bar by x bar into x bar, that is equal to y bar. So yr bar is a biased estimator. Of population mean y bar. This is a biased estimator. Biased means the expectation of yr bar is not equal to capital Y bar. So that is why it is biased estimator. Now we have to find the bias of the ratio estimator. Bias of the ratio estimator BYR bar equal to expectation of YR bar minus Y bar, that is equal to expectation of R cap X bar minus expectation of Y bar, that is equal to expectation of R cap. So because R cap equal to Y bar by X bar, so expectation of R cap into expectation of X bar minus expectation of Y bar by X bar into X bar. So that is equal to expectation of R cap into expectation of X bar minus expectation of R cap X bar. So that is equal to, this is, we know that covariance of xy equal to expectation of xy minus expectation of x into expectation of y. So here we take expectation of R cap X bar minus expectation of R cap into expectation of X bar. This is equal to minus covariance of r cap x bar. So this is the bias of the ratio estimator. Now we have bias of y r bar equal to minus covariance of r cap and x bar. Now that mod of bias of y r bar equal to covariance of r cap x bar. This is mod. That implies bias of y r bar by standard deviation of the ratio estimator. This is equal to covariance of r cap x bar by sigma r cap. That is equal to, we have rho equal to covariance of xy by standard deviation of x into standard deviation of y. So covariance of xy equal to, this is rho sigma r cap into sigma x bar divided by sigma r cap. So this is equal to, since rho is the correlation coefficient and the mod rho less than equal to 1, so this will be less than equal to, that implies bias of the ratio estimator y r bar by sigma r cap less than equal to sigma r cap, sorry, sigma x bar. That implies bias of r cap x bar divided by sigma r cap less than equal to sigma x bar. That implies bias in r cap by sigma r cap less than equal to sigma x bar by x bar. That is equal to coefficient of variation of x bar. So that means this is the bias of the ratio estimator divided by its standard deviation. That means a relative bias is bounded and it is less than equal to coefficient of variation of x bar. And we can see that bias of the ratio estimator, again bias of the ratio estimator equal to minus covariance of r cap and x bar. So the ratio estimator will be unbiased if covariance between r cap and x bar that is equal to 0. That is r cap and x bar are uncorrelated. Now we have to find out the approximate bias of the ratio estimator. Approximation to the bias of the ratio estimator. We have the ratio estimator for the population mean YR bar, that is equal to Y bar by X bar into X bar. So to find the approximate bias, let us define Y bar equal to Y bar plus epsilon 1, X bar equal to X bar plus epsilon 2, where expectation of epsilon 1 equal to expectation of epsilon 2, that is equal to 0. So that variance of epsilon 1 equal to expectation of epsilon 1 square minus expectation of epsilon 1 square, that is equal to expectation of epsilon 1 square. Because expectation of epsilon 1 is 0, that is equal to expectation of epsilon 1 will be y bar minus y bar whole square, that is equal to variance of y bar. Similarly, variance of epsilon 2 equal to variance of x bar. Now equal to y bar by x bar into x bar. So that is equal to y bar plus epsilon 1 x bar plus epsilon 2 into x bar. That is equal to y bar taking common 1 plus epsilon 1 by y bar divided by x bar 1 plus epsilon 2 by x bar into x bar. So this will be equal to y bar 1 plus epsilon 1 by y bar into 1 plus epsilon 2 by x bar inverse. So that is equal to y bar 1 plus epsilon 1 by y bar into, now using Taylor series expansion, we can get 1 minus epsilon 2 by x bar plus epsilon 2 square by x bar square minus up to higher. So this implies y bar equal to y bar 1 plus epsilon 1 by y bar into 1 minus epsilon 2 by x bar plus epsilon 2 square by x bar square, and neglecting the higher terms. So this will be equal to 1 by 1 plus epsilon 1 by y bar minus epsilon 2 by x bar minus epsilon 1 epsilon 2 by y bar x bar plus epsilon 2 square by x bar. Now taking expectation in both sides, we get expectation of y r bar equal to y bar 1 plus expectation of epsilon 1 is 0, expectation of epsilon 2 is 0. So this is 1 1 minus expectation of epsilon 1 and epsilon 2 by y bar x bar plus expectation of epsilon 2 square by x bar square. So this is equal to y bar 1 minus, this is expectation of, this is y bar minus y bar x bar minus x bar divided by y by x bar plus expectation of x bar minus x bar whole square by x bar square. So this is equal to y bar 1 minus covariance of y bar x bar by y bar into x bar plus variance of x bar by x bar. This implies expectation of y r bar equal to y bar plus y bar into variance of x bar by x bar square minus covariance of y bar x bar by y bar x bar. So this implies expectation of y r bar minus y bar equal to y bar into variance of x bar by x bar square minus covariance of y bar x bar by y bar x bar. This implies bias in y r bar equal to variance of x bar, this is y bar into variance of x bar by x bar square minus covariance of y bar x bar by y bar. Now since we are selecting the sample of size small n by using SRSWR, so we have variance of x bar equal to 1 minus f by n into sx square, where f equal to small n by capital N. Sx square is the population mean square for the variable x. So 1 by n minus 1 summation I equal to 1 to n xi minus x bar whole square. So covariance of y bar x bar, that is also equal to 1 minus f by n syx, where syx is the 1 by n minus 1 summation I equal to 1 to n yi minus y bar into xi minus x. Now using these values here, we can get the bias of y r bar equal to y bar into 1 minus f by n into sx square by x bar square minus syx by y bar x. Now if you denote cx equal to sx by x bar and cyx equal to syx by y bar x bar, then this bias will be equal to 1 minus f by n into y bar cx square minus. So this is the expression for the approximate bias of the ratio estimate. Now we can see that this bias is negligible or very small if cx square equal to cyx. That implies cx square is equal to sx square by x bar square, that is equal to syx by y bar x bar. That implies sx square by x bar, that is equal to syx equal to rho sy sx divided by y bar. That implies sx by x bar equal to rho sy by y bar. That implies y bar by x bar, that is equal to rho sy by sx. That implies r equal to, this is beta yx. Beta is the regression coefficient of y and x. That means when r is equal to beta, then the bias of the ratio estimator is negligible and the ratio estimator can be treated as approximately unbiased. Now approximate variance of the ratio estimator. We have yr bar equal to y bar equal into 1 plus epsilon 1 by y bar minus epsilon 2 by x bar minus epsilon 1 epsilon 2 by y bar x bar plus epsilon 2 square by x bar square plus up to so on. Now considering up to the first order of epsilon, this is approximately equal to y bar plus 1 plus epsilon 1 by y bar minus epsilon 2 by x bar. So this implies yr bar minus y bar approximately equal to, this is epsilon 1 minus r epsilon 2, where r is equal to y bar by x bar, the population ratio. Now squaring both sides and taking expectation yr bar minus y bar square expectation, that is equal to expectation of epsilon 1 plus r epsilon 2 whole square. So that is equal to expectation of epsilon 1 square plus r square epsilon 2 square minus 2r epsilon 1 epsilon 2. Now this implies variance of yr bar equal to expectation of epsilon square, that is 1 minus f by n sy square plus r square sx square minus 2r syx, where sy square equal to 1 by n minus 1 summation I equal to 1 to n yi minus y bar whole square. This is population mean square for y variable. Similarly, we can define sx square, and we define syx equal to 1 by n minus 1 summation I equal to 1 to n yi minus y bar into xi minus x bar. So using this in this expression, so variance of yr bar equal to 1 minus f by n into 1 by n minus 1 summation I equal to 1 to n. This is yi minus r xi whole square. On simplification, we can get this yi minus r xi whole square. Similarly, an unbiased estimate of the variance of yr bar can be obtained by 1 minus f by n, this is small y square, plus r cap square s square minus 2 r cap SYX, but this estimator is also a biased estimator. Now this is here we have discussed the ratio estimator, its bias, its approximate bias, and the variance of the ratio estimator up to the first order of approximation. Now in my next lecture we shall discuss about the comparison between the ratio estimator with simple mean estimator under SRSWR scheme. Thank you.